Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan, and I am a chemical engineer. Today we will discuss centrifugal pumps, reducing seal and bearing failures. The mechanical seal of a centrifugal pump in hydrocarbon service is the weak point for any process unit. In 1970s, when I was not born, there were two truths about refinery operations. 1. Engineers hated being operating supervisors. 2. Half of time was devoted to the repair and replacement of pump mechanical seals. Maintenance authorized so much overtime for seal maintenance that they purchased a new fishing boat with their extra pay. In new millennium, mechanical seals are far more costly and complex, but no more mechanically reliable than in 1970s. Their reliability is not a matter of their design, but of the operator's ability to operate, and most especially, to properly start up a pump. A seal may cost $30,000 to $40,000 to repair. Damage to such a seal is cumulative, meaning improper startup or operations may not suddenly cause the seal to fail but will certainly hasten the time when it will fail. A seal should maintain its integrity for 6 years, provided it is operating correctly. Most often seal life is compromised by improper startup procedures. For example, starting up a pump without venting the seal flush lines to the inner seal on a self-flushed pump may reduce the operational seal life by 6 months, even though the seal faces have run dry for only a few seconds. A packed pump. Centrifugal pumps were used in the 1880s. I have a book, Pumps and Pumping by M. Poisbale, published in 1889, which describes centrifugal pumps. A far more timely text, which I prefer because it has easy-to-understand sketches, is Centrifugal Pumps by I. A. Karasik and Roy Carter, 1960. The 1889 text does not mention mechanical seals, as they did not exist then. These early centrifugal pumps were packed pumps. My old shift foreman showed me how to replace the packing for a sour water pump. As Old Man explained, Mr. Khan, the purpose of the packing is to keep the liquid in the pump case from squirting out along the shaft. The packing is this square-shaped asbestos rope. Look here. I cut the rope into 7 lengths. Each piece is just a bit shorter than the circumference of the shaft. I'll wrap each piece around the shaft. But boss, it seems like the liquid in the pump case could squirt out through that gap between the ends of the rope. No, Mr. Khan, see how I place the rope rings around the shaft? I offset those gaps by like 45 degrees, so that the gaps don't line up. Then I'll push the rings into that cavity at the inboard, that is, the side of the pump nearest the driver. See how I'm stuffing the rings into the round cavity? What's the cavity called, boss? Does it have a name? I asked. It's just called the stuffin' box, I reckon. Never heard no other. Next, Old Man continued, we gotta push the rings tight together inside the stuffin' box. That's done with this here lantern ring follower, that is lantern gland. We tighten it up to press those 7 rings of rope right up tight together. Boss, I don't think you got that lantern ring follower particularly tight. Maybe you should just pull up on those gland studs a bit more. Old Man smiled and said, nope. That ain't right. I'll just show you, Mr. Khan. Old Man switched on the pump's motor and studied the stuffing box. It's not leaking enough. If it doesn't leak some, it means those rings are packed too tight. Too much friction of the packing rings pressing on the spinning shaft. Packing will overheat. Wastes power and damages the shaft and packing. Also, needs some leakage to keep that packing lubricated. See, I'll just back off some on the gland studs. Let a bit more water leak out. That looks just about right now. You can do the next one, Mr. Khan. It's that old cooling water pump on number 1 alkalinity. I'll watch and you do it. Mechanical seal. Boss, I asked over dinner that evening, seems like those packing rings have to leak to cool and lubricate the inside of the stuffing box. Fine for water or even cold diesel. but not so good for butane or gasoline. Yep. Packed pumps have their limits. Not any good when pumping stuff that don't lubricate, like propane and butane and such. Not too safe if stuff that leaks out can catch fire easy like gasoline. Or is bad to breathe, that is, carcinogenic, like benzene or rich amine with H2S. Or can set up like wax. Then we gotta use a mechanical seal. How does that work? I asked. Well, old man answered, those mechanical seals, they have two faces. They're made in the shape of rings. One ring is soft. It's made of carbon. The other ring is hard. It's made of tungsten carbide. One ring is stationary. It's fixed into position on the pump case itself. It's kinda part of the pump case. The other ring rotates with the shaft and the impeller. It's kinda part of the pump's rotating assembly. Mr. Khan, those two rings or seal faces are pressed together by a strong spring, called the bellows. I guess, boss, the bellows are like the lantern ring follower we adjusted with the packed pump. Adjusts the pressure on the seal faces. That's right, Mr. Khan. Same idea. Where these faces run past each other, that's the seal. Keeps the liquid in the pump case from running out along the shaft and escaping out into the air. Purpose of seal flush. Boss. If the seal faces run past each other and are pressed together by the bellows, I would think they would get really hot, just like if we over-tighten the lantern ring follower on the packed pump. Why doesn't that also happen to the mechanical seal? It certainly could happen, Mr. Khan, except that seal flush liquid keeps the seal cool and lubricated. The seal flush liquid flows round the outside of the seal faces, along the shaft, and back into the pump case. Okay. But where does the seal flush come from? Out here, on our alky unit, most of the pumps are self-flushed pumps. That means the seal flush liquid comes from the discharge of the pump itself. Old man sketched the drawing to explain, which I've shown in picture. Boss, it seems like you're saying that the seal itself is full of high-pressure liquid from the pump discharge. Won't that put an awful lot of pressure on the seals and cause them to leak? No, Mr. Khan. You ain't looking at my sketch. See how that seal flush liquid comes through the restriction orifice? That orifice is just big enough for a couple GPMs to flow, 1 or 2 GPMs per inch of shaft diameter, into that seal flush chamber. The seal flush chamber is like the old stuffing box on the packed pump. That little seal flush flow leaks back into the suction side of the pump case through the holes in the back of the impeller. I guess, boss, that means the seal operates just above the pressure inside the pump case, which is a little below the pump suction pressure, I said. Externally flushed pumps. Boss, I've got another question. When I worked on our paving asphalt plant last year, did the asphalt pumps also use that black tar as seal flush? I asked. No, old man answered. Those were external flush pumps. Wouldn't want to get tar between them seal faces. Those pumps were flushed with diesel oil or light gas oil. On that kind of pump, the operator needs to adjust the seal flush pressure a few psi above the pump suction pressure. Best to have a little needle valve and a rotometer. Also, you gotta have a pressure gauge after the needle valve on the seal flush line. But boss, the diesel used as the seal flush liquid will leak into the asphalt through the holes in the back of the impeller. That surely is a problem. That's why on external flush pumps, you gotta be really careful not to use too much seal flush pressure. Also, the seal flush liquid gotta be a kind that won't ruin the product being pumped if it contaminates a little. Seal leaks. The main advantage the mechanical seal has over packing is that it's designed not to leak. If it does leak a little, then the material that escapes from a self-flushed pump is the product. For an externally flushed pump that is leaking a few GPM, the material escaping is the seal flush liquid. For an externally flushed pump mechanical seal that is blown, that is, leaking really badly, the product being pumped is escaping along the shaft. In refineries, this is both dangerous and environmentally objectionable. The factors that cause mechanical seals to leak are numerous. Loss of seal flush flow. Particulates in seal flush. Pump vibrations due to cavitation. Pump vibrations due to bearing damage. Uneven heating of pump case prior to startup. Loss of pump suction pressure on pump startup. This, in my experience, is the single biggest contribution to reduced seal life. Leaving a pump idle, that is, several months, for too long. Ice crystals when pumping wet propane or butane that form between the seal faces. Failure to fill the seal flush line prior to starting the pump. Excessive seal flush pressure. A pump seal ought to last about 6 years. Running a seal dry for a few seconds during startup can reduce the seal life by 6 months. For a self-flushed pump that loses suction pressure on startup, there will be little or no seal flush pressure until a normal pump suction pressure is established. Also, a pump that cavitates on startup, due to the loss of suction pressure, will vibrate, which also contributes to the damage to the pump's mechanical seal faces. If the radial support bearings are damaged, the resulting vibrations will be transmitted to the seal and damage the seal faces. Water contamination of lube oil in the bearing house is the most common cause of bearing damage. A pump case in hot service should be heated evenly prior to starting or switching the pump. This is usually done by the warm-up valve on the pump discharge. This valve bypasses the discharge check valve, thus permitting the hot liquid being pumped by the primary pump to back into and preheat the spare pump that is being put online. Leaving a pump in one position for months will dry out the bearings and cause temporary distortion to the bearings and pump shaft. Running the pump for a few moments will correct these minor problems. But, during the run-in period, the vibrations may damage the seal faces. Operating experience indicates that switching pumps every week is far too frequent. Switching pumps once a year is far too infrequent. The optimum seems to be to run a pump every few months. Several smart people suggest that the primary pump should be run 90% of the time, while the spare is run 10% of the time and kept on partial standby. To keep ice crystals from pushing the seal faces apart, due to auto-refrigeration of the seal faces when pumping wet propane or butane, I used to keep a wisp of steam blowing onto the stuffing box to melt any ice crystals. I learned this nice trick from old man. Particulates in the seal flush can scratch the seal faces. I've never actually encountered this problem myself, but it can be prevented by installing a Centrifugal filter on the seal flush line. On one hydrocarbon pump, the restriction orifice was omitted from the seal flush line. This greatly increased the pressure on the seal faces. The seal blew out with a large and quite dangerous emission of hydrocarbon vapor to the atmosphere. For self-flushed pumps, it is necessary to vent and fill the seal flush lines completely. Otherwise, on starting the pump, there will be no seal flush flow for a second or so, which will materially damage the seal. For externally flushed pumps, this is not a problem as long as the seal flush is commissioned before the pump is switched on, which is a problem. Wasting external seal flush oil. When a pump is not in operation, it is not necessary to have the seal flush flowing. Obviously, for self-flushed pumps, this is not a problem, as the seal flush flow stops with the pump. But for externally flushed pumps, there is no sense leaving the seal flush running. For example, let's say I'm operating a delayed coker or vis breaker charge pump. The seal flush flow for such a pump, all of which flows back into the pump suction when the pump is idle, would be 1 or 2 GPM per inch of shaft diameter. For a 2-inch shaft with both inboard and outboard seals, that's 400 BSD. If the seal flush is clean gas oil, 400 BSD of gas oil will be recycled back through the coke drums or visbreaker soaker coils. At $15 US a barrel downgrading cost, that's $6,000 US a day. All to no purpose. Just remember to turn the seal flush back on before restarting the pump. In black oil service, I've seen asphalt plant operators wait a few minutes after a pump is shut down before they block in the external seal flush flow. Of course, for auto-start pumps, leaving the external seal flush closed is not an acceptable option. But, in the above example, maintain the auto-start option is costing $2 million a year in degraded product yields. I suppose that's the justification for nitrogen barrier seals, as described below. Double mechanical seal. A self-flushed pump with a single set of mechanical seal faces can leak the process fluid into the environment. If the process fluid is hydrocarbons, this sort of leakage is no longer permitted by the EPA. The sketch I have shown in picture does not represent the actual configuration of a double mechanical seal component but does explain the function of the individual pump internal components. The components of the pumps to the left of the inner seal faces are the same as that which I have previously described for a single mechanical seal. However, let's go through the function of each component starting at the left side of the sketch. Impeller accelerates the process liquid. Pressure balancing holes allows seal flush liquid that escapes past the throat bushing to flow back into the suction of the pump. Throat bushing holds back pressure on the seal flush liquid against the inner seal faces, or helps to control the flow of seal flush liquid, along with the restriction orifice. Filter removes particulates from the seal flush flow. Not always needed. Cooler removes heat from the seal flush flow. Not always needed. Restriction orifice reduces the seal flush pressure to slightly above the pump suction pressure. Inner seal prevents the inner seal flush liquid from escaping along the shaft into the space between the inner and outer seals. Inner springs presses the rotating inner seal face up against the stationary inner seal face. Reservoir holds the outer seal flush liquid. Pumping ring helps circulate the outer seal flush liquid. Disaster bushing, in case of a catastrophic seal failure, reduces the flow of process fluid to the environment. Outer seal prevents the reservoir liquid from escaping along the shaft into the environment. Outer seal flush cools and lubricates the outer seal faces. Bearing housing holds a pair of bearings, the lube oil, and slinger ring omitted from sketch. Lip seals, also called dust covers or carbon seals, retards contamination of lube oil with dirty and humid air. Breather cap permits air accumulated in the bearing housing to escape. Water sediment bulb and petcock is used to drain water out of the bearing housing. The double mechanical seal does not really improve the reliability of the pump seal. In case the inner seal begins to fail, the level and pressure in the outer seal reservoir will increase. An alarm should sound in the control room alerting the operators of the seal failure. As the reservoir pot is vented to the flare, this should prevent small seal leaks from escaping directly into the environment. The fluid that circulates between the two sets of seal faces is an environmentally safe liquid such as glycol, which is called the buffer fluid. It's circulated by the pumping ring. The reservoir may have a nitrogen makeup pressure control, cooling coil, and back pressure control switch. I haven't shown these details. The main purpose of the double mechanical seal is to alert the operator that the inner seal has failed. Dry seals. One method of totally eliminating the use of externally flushed pumps using single mechanical seals is to use nitrogen barrier or dry seals. The seal faces are machined using a special technique. Nitrogen is then pressurized into the seal chamber and between the seal faces. These seals are very expensive, double the cost of conventional seals, and the feedback I get from my clients is mixed. For self-flushed pumps, nitrogen barrier seals would serve no purpose. Also, if a loss of flushing oil into the process fluid is not uneconomic, I would stay with a conventional seal. In refineries, I would use nitrogen barrier seals in vacuum tower bottoms, coker feed, vis breaker feed, residual extraction, ROS, resid FCU feed. The amount of nitrogen actually consumed is very small, and certainly does not affect the process itself. Perhaps 1/3 to 1/2 of my clients react with hostility when I suggest the benefits of N2 seals, based on their experiences. One of the problems with the use of ordinary N2 barrier seals is that they will be ruined if a pump spins backward, even briefly. This will happen when a pump is shut down after turning on the spare pump, if the discharge check valve leaks. The solution to this problem is to install bidirectional N2 barrier seals, which are designed to rotate in both directions. Considering that someone may leave open the warm-up valve around the check valve, when a pump is shut down, this may be a good investment. Application of nitrogen barrier seals using double mechanical seals. A dry or nitrogen barrier seal is typically used as the outer seal on a double mechanical seal shown in picture. Double mechanical seals are used when the process fluid is environmentally objectionable or above its auto-ignition temperature. The nitrogen barrier seal replaces the reservoir fluid, providing seal flush lubrication to the outer seal in the more conventional double mechanical seal. As the inner seal for an externally flushed pump, such as a black oil, that is, asphalt, resid, pump will continue to have the same loss of seal flush material to the process stream through the throat bushing with the conventional double mechanical seal as when the external seal is an N2 seal. There is no real process incentive for use of the more costly N2 seal. Theoretically, dry seals have a longer operational life than seals using reservoir fluid to lubricate the outer seal. In practice, in my experience, this is not the case. I've accumulated a partial list of some of the problems relayed to me by the operators at the plants, summarized in the following section. It is possible to use N2 on the inner seal and replace the external seal flush, but this is not a common practice and reportedly is quite costly. As dry nitrogen barrier seals are about twice as expensive as a conventional seal, it's rather difficult to see the justification of the incremental cost. Problems with nitrogen barrier dry seals. I was taking a course for operators last week, and they had a host of complaints about N2 seals. 1. The nitrogen causes an idle spare pump to gas up and makes it difficult to switch pumps. 2. If the seal faces become wet with sour water, when a pump is taken out of service for maintenance, the seal may be damaged. 3. If the seal flush can be water, that is, sour water or amine, the dry seal design serves no purpose. 4. If the pump runs backward, most, not all, nitrogen barrier seals will be ruined. 5. Shouldn't cooling tower and other water pumps just be packed and not have any mechanical seals, N2 or otherwise? Why then have our water pumps in this service been modified at great expense to double mechanical seals? Asked an older operator. Steam use in seal chamber. Sometimes low-pressure steam is connected to the pump stuffing box or seal chamber. I used to think that this steam was being used in the same way that nitrogen is used in a dry seal. This is quite wrong. The steam was being used for an entirely different purpose. It's there to help keep the bellows, that is, the spring assembly that is used to compress the seal faces, cool and clean. Hence, this steam pressure should be only a little above the pump suction pressure. In black oil services, the outside of the bellows can clog up with dirt without this flow of purged steam. Then the bellows would be unable to apply the proper pressure to the rotating seal face. Pressure balancing holes. Referring to picture, note that the seal flush liquid enters the pump case between the rotating face, for internal assembly seals, and the back of the pump's impeller. The idea is for the relatively small flow of the seal flush liquid to flow back into the suction of the pump, and thus be returned to the process steam. Incidentally, for external assembly seals, the fixed face is closer to the impeller. For many impellers, holes have been drilled in the back face. These are called pressure balancing holes. They prevent the accumulation of pressure behind the mechanical seal. This could cause the seal pressure to exceed the pump section pressure, which would overpressure the seal faces. One of my clients that pumps hydrocarbons contaminated with solids has observed that these pressure balancing holes often plug. This will cause the pump seal to be damaged. This client has typically purchased mechanical seals designed for the pump's discharge pressure to avoid seal failure when the impeller balancing holes plug. Only a few % of my clients design seals for the pump discharge pressure, rather than follow the more conventional practice of designing the seal for the suction pressure. Bearing failures. The pump bearings support the weight of the shaft. Most pump bearings are ball or roller type. For larger pumps with double suctions, that is, balanced impellers, there will be both an inboard and outboard bearing. For most of the smaller pumps, that is, overhung, with only a single suction connection, there will be a pair of inboard bearings, both located in the bearing housing. Any damage to the pump's bearings will cause vibrations that will be transmitted to and damage the pump's mechanical seal faces. The usual causes of bearing damage are moisture in the lube oil, low lube oil level in the bearing housing, excessive oil level in the bearing housing. In the wet sump system of bearing lubrication, the oil level should be kept just a bit below the bottom of the bearing. There is a loose ring in the bearing housing that slings the oil around. It's called the slinger ring. There's a sight port on the side of the pump case to see this lube oil level. Inside the oiler glass itself, there is a screw to make fine adjustments to the oil level. Within plus or minus a quarter inch, I don't think the oil level is all that critical. Excessive oil level, like halfway up the shaft diameter, will trap heat in the bearings and cause them to overheat. Moisture is drawn into the bearing housing due to the rotation of the shaft. This moisture will accumulate in the bearing housing and ruin the lubrication properties of the lube oil. In picture, I've shown a water sediment bulb that I've used to drain water from the bearing housing. This is not a complete solution to water contamination of the lube oil. The oil and water will become emulsified in spite of water being drained from the bottom of the housing. It's easy to watch this problem develop. The oil level in the oiler glass increases due to the water, rather than slowly decrease, which is normal. Oiler glass level discrepancies. Sometimes the oil level in the oiler cup or glass is quite high, but the real oil level in the bearing housing is too low. I can think of 4 factors that can cause this problem that result in pump bearing damage. 1. The oiler glass should be located upstream of the direction of rotation. By upstream, I mean that if you are looking at the outboard end of the pump and the impeller is rotating clockwise, the glass should be on the right-hand side of the pump. Locating the oiler on the other side causes the oil to be slightly pushed up into the glass. That is wrong. 2. The bearing housing breather cap is plugged. Air is pushed into the bearing housing by the spinning shaft. The resulting air pressure in the housing can push the oil up into the glass. This breather cap needs to be periodically cleaned. 3. The connection between the oiler glass and the bearing housing plugs. 4. Moisture from the humid air drawn into the bearing housing condenses and displaces the oil upward into the oiler glass, as discussed. Many years ago, working as an outside operator, I noted that on some of my steam turbine-driven pumps, the level of oil in the oiler glasses rose perhaps 1/2 to 1 inch every day. I actually thought that in some mysterious way, that lubrication oil was being produced inside the bearing housing. Of course, it was just water. I'm older now, and much wiser. As discussed in the following section, use of an oil mist lubrication system eliminates all of the problems with erroneous oiler glass level indications and with moisture in the lube oil. Oil mist system, bearing housing. My experience is only with the wet sump system for bearing lubrication. This means there is an oil level of several inches in the bearing housing. The oil level should be a fraction of an inch below the bottom face of the bearing. This level can be precisely controlled with a screw adjustment inside the oiler glass located on the side of the bearing housing. However, I now understand that the oil mist lubrication system is superior to the wet sump system. In the oil mist method of bearing lubrication, a small stream of air containing atomized lube oil is blown continuously into the bearing housing. There is no liquid level maintained in the bearing housing, which is kept completely drained. This eliminates the two main problems with the more conventional wet sump lubrication system. Operating errors associated with improper lube oil levels are eliminated, as there is no level to maintain. The problem of water contamination of the lube oil due to moist air being drawn into the bearing housing by the spinning shaft and leaking bearing housing dust covers, that is the lip seals, is totally eliminated. Water infiltrating into the bearing housing will emulsify with the oil, and thus degrade its lubrication properties. With a totally drained bearing housing, water is immediately drained out of the bottom of the housing. A large number of pumps can be lubricated from a centralized oil mist atomizing station. The design and construction of such a system is an additional and expensive project complication, compared to having an oiler glass on each pump. But, on the other hand, anything that reduces the probability of operator error is sure to increase unit reliability and reduce running-up maintenance expenses. It is standard practice to have an automatic backup system for the oil mist generator. Water accumulation in the bearing housing of turbine-driven pumps. An old man taught me the following neat trick. A turbine driving a pump with an inboard bearing, which is normal, starts to blow steam out along its shaft, due to a defective gland seal. The steam impacts the inboard end of the bearing housing. The rate of water accumulation in the pump's bearing housing increases by an order of magnitude. To retard the moisture accumulation in the bearing housing, one takes a hose with dry plant air and blows it across the shaft between the coupling and the pump's bearing housing to push the steam away from the bearings. Old man was just a sulfur plant shift foreman. But he was one of the most valuable employees of Refinery. Another trick that I have learned recently that also helps to extend the bearing life, if an oil sediment bulb is not used, is to employ a magnetic drain plug. This helps to collect any metal particles in the oil reservoir so as to prevent them from becoming a hazard to the bearings. Cloudy lube oil. If water is kept drained from the bearing housing using the water sediment bulb shown, bearing life can be extended. Once the oil takes on a cloudy appearance, 0.1% water, the bearing life can be reduced by a factor of 4 to 10. I screwed the small water sediment bulbs into the half-an-inch cased drain on my pumps. I never actually looked for water in the bulbs. I would just drain a little fluid through the petcock to see if the lube oil was free of water. Then, if the level in the pump's oiler glass dropped a bit, I was satisfied that the connection between the glass and the bearing housing was not plugged. For plants equipped with a lube oil mist system, the bearing housing has no liquid level, so water contamination of the lube oil cannot happen. One thing I did not do was clean the bearing housing breather cap. Thus, some of my pumps would develop a slight positive pressure in the bearing housing, which pushed up the oil level in the oiler glass and pushed down the level in the bearing housing. I remember being mystified as to why the levels in the oiler glasses would increase by themselves over a period of a few days. Continuous water or air accumulation in the bearing housing is an indication that the lip seals, or dust covers, need to be replaced. These lip seals are not expensive, and their replacement is quite simple as shown in picture. Starting a centrifugal pump. The objective in starting a centrifugal pump is to minimize the damage to the pump's mechanical seal during startup. The facilities required for this purpose are: pump suction pressure gauge downstream of the pump suction strainer, vent and valves to remove vapors from the seal flush system, shown as valves 1, 2, and 3 in picture, a half-an-inch drain valve on the bottom of the bearing housing, or water sediment bulb, a high point vent on the top of the pump case. For larger pumps with the suction on top of the pump case, a spillback warm-up line connected to the case is needed to evenly warm up the pump. For all hot pumps, a spillback bypass is needed around the pump's discharge check valve for warm-up when switching pumps. Preparation before starting a pump. 1. For an externally seal-flushed pump, open the seal flush flow and adjust the seal flush pressure to the manufacturer's recommended pressure above the suction pressure. If this data is not available, use the pump suction pressure plus 10% of the pump's normal differential pressure. The seal flush pressure should not be close to the discharge pressure. This will damage the seal. 2. For the more common self-flushed pumps, vapors trapped inside the seal system tubing and coolers must be vented out and displaced with liquid. Otherwise, lubrication between the seal faces will be intermittent during startup. A few seconds of running a dry seal can cause a year's worth of wear on the seal faces. Do not assume that because you have started up a pump without blowing the seal before, that no damage has been done. 3. Clean out the pump suction strainer. Check that the suction pressure gauge is operable, and that the connection is not plugged. The unit engineer should have placed a red mark on this gauge showing the minimum required suction pressure to prevent cavitation on startup. For pumps that have an oiler glass, that is, not used on the oil mist system, drain half of a glass, a few ounces of lube oil from the bearing housing. A bubble of air should rise in the oiler cup or glass and the cup level should drop a bit. Drain out all water and make sure the oil drained is clean and not cloudy. If not, damage to the bearings will cause vibration and damage to the seal faces. 5. Vent the top of the pump case to fill the case with liquid. For a self-flushed pump, starting with gas in the pump case will contaminate the seal flush tubing and cooler with vapor. 6. Open the spillback around the discharge check valve to warm the pump case. For pumps with the suction on top of the pump's case, open the connection allowing the hot spillback flow to recirculate to the bottom of the pump. The suction valve needs to be partly open. Wait until the pump case is uniformly warm. Starting a pump that is cold or unevenly heated will cause uneven stresses on the seal faces, or high viscosity liquid will remain between the seal faces to shear the seal faces. This step only applies when switching pumps, and not for a complete unit startup. Startup. 1.it takes a lot of energy to accelerate the liquid in the suction line of a pump. The longer the suction line, the more energy is needed. The energy does not come from the pump, but from the pressure of the liquid itself. Thus, the pressure at the pump suction will drop radically if you open the discharge valve too quickly. This will cause the liquid to vaporize inside the pump. That's cavitation, which is sure to damage the seal faces. The faster you open the discharge valve, the greater the reduction in suction pressure. 2. Opening up the discharge valve too slowly is also bad. Running a pump at an extremely low flow will cause vibration, overheat the seal, and dry out the faces. 3. So open the pump discharge valve as rapidly as possible, consistent with not permitting the suction pressure to fall below the red mark on the pump suction gauge, that is, minimum pressure to avoid cavitation on startup. Do not be guided by the pump discharge pressure. By the time the discharge pressure becomes erratic, vapor is already being generated inside the pump case with consequent damage to the seal faces. 4. Running a pump in a cavitating mode during startup may not damage the seal faces to the extent that the seal will fail. However, a year's worth of life from a seal can be lost in 1 minute due to cavitation on startup. Improper pump startup is like cigarette smoking. The damage is cumulative. Switching pumps every month or two is a good idea to extend seal life. But not if starting up the idle pump is done improperly. Then, the seal life will be shortened even further. Pumps that sit idle for more than 3 months will cause bearings to be damaged when the pump is restarted. Additional valving for startup. The valving referred to in my startup procedure is not provided in most applications. To evenly warm up a large pump with the suction on top, you will have to install a connection from the warm-up line to the case drain at the bottom of the pump. If the pump case is not warmed up uniformly, this will cause the seal faces to misalign during startup. Referring to picture, in addition to valve 1, the valves shown as valves 2 and 3 must also be added. Without valves 2 and 3, the complete seal flush line cannot be filled with liquid. For externally flushed pumps, valves 2 and 3 are not required. For pumps with double mechanical seals, the fluid level in the reservoir should be checked. The correct level is in line with the reservoir return nozzle. Too low a level will reduce the fluid circulation rate. That's all, gentlemen. If you like my video, please follow my YouTube channel Petro Intelligence for more videos. Good day and good luck.